All right, so I'm going to show you a little bit more, I think, than I normally would related to Pascal's triangle, just because it's stupid powerful. So just to remind everybody, real quick, here's Pascal's triangle. It's a little off kilter here, but oh, it's really bad, Jeff.
Wait, what lesson is this?
Say again, sorry?
What lesson is this?
What lesson?
Yeah, like, is it point?
Oh, I'd say it's chapter 2 going into chapter 3.
Oh.
So it's like, it's section 3-1.
Okay.
Yeah. We're expanding on what we did in chapter 2. Does everybody remember this, if you were here last time? So 1 plus 1 is 2, 1 plus 2 is 3, 1's on the outside, yes? And if I were to do x plus 1 cubed, we did this last time, it would be x cubed plus, come and think, x squared plus x plus 1. 3, 3, there, 1, 3, 3, 1, 1, 3, 3, 1. So if you were to multiply x plus 1 by itself and then by itself again, you would end up with that. We did that last time. So how would I get x plus 1 to the 4th? Do I have what I need in terms of coefficients?
Not yet.
Yeah, so 1's would go on the outside. What goes here? 4. 6. 4. So it'd be x to the 4th plus 1x to the 4th plus 4x cubed plus 6x squared plus 4x plus 1. Okay. Do you all agree that's a huge time saver? Does it take long to kind of like go down to the line you want? As long as it's not to the 848 power, yes? Kind of, and you're not going to see an 848 power where you have to do this. So we're good. So let me go one step further because this really hides a lot of things. What's the coefficient of the x?
1.
1. What's the number at the end?
1.
All right, that's a little too easy. I just want to go a little bit further. It's further than we need for the immediate thing we're about to do. But for some reason, I don't care. Because this is just good to know. So what if instead I had this? Let's make it work. There, 3x minus 4 cubed. Here's the real, full idea of Pascal's triangle. If you wrote that 3 times, the biggest degree would be, let me see if you guys are with me on this. If I wrote this 3 times, do y'all understand there's no way to just do that direct? If I ask you, what is 2 times 6 times 5? Can you do that in one step? No, you can't. I don't care who you are. You might have memorized what that shit is, but you didn't actually do it. How would you do 2 times 6 times 5? 2 times 6. Or even better, 2 times 5 times 6. Yeah. Okay. You guys kind of with me? You have to do it one at a time. But, understanding that, do you all agree there would be a bunch of mixes and matches? The highest degree would be when I end up doing this times this and then times this. Yes? So what this really means is I have nothing but the first dude and then a mixture and then nothing but the last dude at the end. What would be at the end of this? That would be at the beginning. At the end would be what? Negative 4 times negative 4 times negative 4. So at the end, I get nothing but negative 4s. So this is such a cool idea. I have to show you this. And again, like I just said, this actually will not come into direct play in this class right now. Could it in the future? Hell yeah. Could it show up anywhere you wanted it to? Yeah, because it's freaking useful as shit. So this is such a beautiful idea. So when I go to do this, I'm going to have nothing but 3x. I'm going to have nothing but 3x's. I'm going to have 3x times 3x times 3x. Let me just do this all the way out. Plus 3. These tell me my coefficients. 3. I lose a 3x and I gain a negative 4. That would be like this times this times this. I really, really want you guys with me on this. If I were to multiply the shit out, won't I get this times this in here? Won't I eventually multiply what I just got by this? But don't I get it here and here? Don't I get 3 of them? 3 of them? Okay. So this is just realizing the pattern of what happens if you did multiply it out. And we go, we're humans. We're geared to find patterns. This is for us. It's just patterns. So what's the next thing going to be? Plus another 3. Lose a 3x. Gain, Jeff, lose a 3x. Gain a negative 4. Plus 1. Lose a 3x, so I have none of them. Gain a negative 4. So then I get 27x cubed plus, well, it'll be minus, right? 9 times 3 is 27, times 4, I believe, is 108. And it'll be negative. So minus 108x squared. I don't know if you guys are really with me still, or ever. Okay. 9 times 36 is 144, I believe. So I get plus 144x because negative squared is positive, and then I get minus 64 because that's what 4 cubed is. That is a shit ton quicker than right? Whatever sound effect you want to use. I don't know if you guys are really with me. That just kicks so much ass. Especially if the things you're doing don't have the 3 and 4. Then it's stupid easy. So, how does this help us, dear God, Jeff? Stop with your math boy shit and just tell me what I need to know for this class, man. Here we go. I want to know, have you ever seen the right now? I want to know, what is the derivative of this? First question for you is, what the shit is that? What is n? I think I've defined n for you guys. Natural number. Natural number is 1, 2, 3, yes. Now to be really honest, it's a whole number because it could be a 0 power, but we'll be okay. So what I'm trying to do right now is develop a rule for something that is in this form, and then we're going to expand it. But let's just stick with what I just said. How would I do it based on what we did in chapter 2? What is the way to get the slope of a function, which we know is called, I'm pretty sure I made this formal, didn't I? It's called the derivative. I made that formal? What symbol do we use for the derivative, by the way?
F prime.
So we're trying to find f prime. And a symbol, this is the symbol we use most often. This is the symbol that is very often more explanatory. Both of them mean the exact same thing. The way I read this is d by dx. So the df dx. So I'm applying d by dx to f. And this just means do the whole slope thing. That's what that little symbol means. These mean the same exact thing. This one's really nice because you can see the change in outputs over the change in inputs, which is what slope freaking is. What's the process? You can look in your notes. We're not doing a quiz, but does anyone remember the process? It's a limiting process, right?
Plus h.
Yes, the limit as what goes to what?
As x approaches, h approaches 0. F
y2
plus h.
minus y1 over x2 minus x1. I desperately want you to understand, everything we're learning in this class is built on the back of algebra. It's all just extending algebra. That's really all it is. You're gonna get to a point where you're like, I don't care, that's all it is, man. This is weird shit. I agree. But it's built off of this. What is f of x plus h in this case, in this very specific case?
X plus h.
Yeah, just replace x with x plus h. I'll get people tell me this. I'll get people tell me f of x plus h is x to the n plus h. Does everybody see that's very wrong?
Why is it wrong?
Here's why it's wrong. If f of x is x to the n, what is f of 5?
5 to the n.
5 to the n, yes? Yes? So what is f of 2 plus 3? 2 plus 3 to the n. I can't have a plus 3 outside because then it's not really acting on what I put in. So the function has to act on what I put in. And what is the function defined to do? Anything I plug into it, what does it do to it?
Raise it to the power.
Raise it to the nth power. So whatever the shit I put into it, it better take it and raise it to the nth power.
Okay, so you don't, so you just putting it in is gonna raise it, anyway, so you don't put it in the end. That's all. Cause you just plug it in and would raise it to that power.
Yes, but just to be really clear, so this is wrong. F of x plus h will be x plus h to the nth power.
Oh, okay, that's what it equals.
Because what does the function do to anything? Raises it to the nth power.
Okay.
Okay. And then, okay, so if you guys are cool with what's going on. So limit as h goes to 0, x plus h to the n minus x to the n all over h. Now what sucks for me is if I'm not careful, my n's look like h's. I appreciate that. Oh, I'm so happy when somebody else is like, I have the same problem, John. Oh, good.
My A's look like 9s all
Me too. My S's look like 5s. And my students love it. They love it. They're like, this is so clear. This is as clear as mud. Thanks. I'm so happy I took this guy. All right. So everybody understand, not much has happened yet. We were given a function. We put x plus h into it. Didn't matter if it wanted it in there, now we just put it in there. And now here is the form of figuring out the slope, the derivative. Yes? How the shit? So, what I really want you to understand is, I would have to go to where?
And
To the nth. What's going to be the first coefficient?
what?
1. What's going to be the next coefficient? You could do it. You could do it. Here's 0, here's 1, here's 2. That's x squared, right? Here's 3. You can do it, you can do it. I need you to understand. So is everybody with me? If I do x plus 1 squared, it'll have a coefficient of 1, a coefficient of 2, a coefficient of 1, correct? So when the power is squared, what's the second coefficient? 2. When the power is cubed, what's the second coefficient? 3. When the power is nth power, n. Now what's going to be after n is weird shit. Yes? But it's going to be some function of n. Yes? N business. Yes? Is everybody with me? I love you guys so much.
Thanks.
You're welcome. I don't know if you guys are really with me. So if I do x plus 1 cubed, I get x cubed plus 3x squared plus 3x plus 1. The second coefficient and the second to last coefficient will equal the power that you started with, just because of the way that things get put together. When I square something, I put them together twice. When I cube something, I put them together 3 times. Blah, 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 blah. Okay. Are you ever going to have to do this by yourself? No. This is not an example problem. We're developing a rule that we will use for everything. All stuff that looks like x to the n, I can use this rule for. So look what, let me see. I've got this on my little handout too, so. If I start to write what this is, the idea of binomial expansion, of Pascal's triangle helping me, is I'm gonna start with nothing but these, correct? I'm gonna start with n x's plus next coefficient, 1 less x, 1 more h. That's the idea, yes? Plus, do you understand now every term after this, how many h's will it at least have? 2. So the next one is going to be some coefficient based on n, x to the n minus 2, h squared, yes? So read with me. And then plus all stuff that have at least 2 h's in them. In this case, 3. Okay. Does everybody understand that? So the idea of expanding this kind of thing is you start off with nothing but this, then you make a mixture. So I always think about this, nothing but x's, no h's. 1 less x, 1 more h, 1 less x, 1 more h, 1 less x, 1 more h, 1 less. That's how that kind of works. And at the end, you have nothing but this last dude. So at the very end of all this shit, it's going to be h to the n. All over what? And I forgot something. Will be h. And this was just this part, right? So this is minus x to the n. I am the king of leaving enough room. So everybody think minus x to the n, is that cool? So what immediately happens on the top? Even though the top looks freaky as shit, what definitely happens? I lose the x to the n, yes? Everything left has at least one h on the top. You with me? So can I divide by h?
Yeah.
Of course I can. Everybody can lose an h, yes? So then I get if this guy loses an h, it's just this guy, yes? Yes? Whatever you say, Jeff. Plus, if this guy loses an h, is this business times h, yes? Plus, everything else has at least 2 h's, yes? And I'm going to let h go to
0.
so the only thing left at the end is going to be the one piece that didn't have an h anymore, correct? I love you guys. Everything else going to go to 0. Going to go to 0, yes? Okay. So at the end, I'm going to get this. Oh, this is, oh, I see.
I thought that was H4, N4.
I'm with
and it
you.
was like
It's
a
minus 1,
N
yeah.
minus 1.
The n minus 1 is because as I move through, I lose an x, gain an h, lose an x, gain an h. So I start to lose those. Yes. Where are we at?
X.
No, it's a plus, I'm sorry. I've got all of this on the handout, by the way. I've got this again on the handout, like generated by computer. You can tell why I don't write up my own handouts. Because this is bad enough. Okay. So what the hell did we just learn? We learned that if I'm given x to the n, the derivative, look what happens. What does it look like happens? We got it to be this. What does it look like happens? And this is a way to remember it. The power
Went down.
comes down, and then it goes down by 1. Some of you guys have taken a little calculus before, so I can see you out there like, yeah, I know this shit, but of course you know this shit. This is new to the rest of us. This is a consequence of the limit definition. How do you find the derivative of anything? Limit definition. Are we going to use that forever? Thank the gods, no. I don't want to use the limit definition for everything. Holy shit, can you imagine doing the limit definition for, well, we're going to do sine. That's going to be hard enough. But we'll see. Okay. Or maybe cosine again. In fact, all right, so let's immediately do some examples. So what if I had this? Don't say anything out loud. Apply the rule. Don't say anything out loud. What's this derivative? Don't tell me. Believe it or not, sometimes I'll have somebody still tell me the answer after I said that many times. This will become one of your favorite rules ever. It won't be your favorite rule. You'll see an even better one here eventually. So how does that work? What happens? Yes. The very first thing I should say is this is in this form, yes? We're going to learn derivative rules. Derivative rules? What is this, Jeff? Is this a beer? No. We're going to learn derivative rules. You have to have the function in the right form to apply the rule. So this is in the right form. The 7 comes down. 6 power. And I have no idea. I don't know if you guys remember. Do you guys remember when we did a function like this and we graphed its derivative and we ended up with a parabola looking dude? And I pointed out at the time, it looks like the power goes down by 1. It was a cubic and then it became a squared. Yes? So that graphical prediction has been borne out by the math. Fantabulously. Maybe? And you guys look beat up, I'm sorry. What do you guys think about this?
Let's see.
Do you all agree that derivatives are fundamentally a limit process? Yes?
Sure.
Okay. Not even agree, just it is. Okay. This is how you define the derivative. It's the limit as h goes to 0 of stuff. Okay, it's a limiting process. If I take limits and I have a constant multiplied by my function, can't I just take that out? Remember that? No? What's the derivative of x to the 11th? The 11 comes down, and it's raised to the what power? If there's already a number out front, and to be honest, we just did that, to be honest. What's in front of x to the 7th?
1.
1, and didn't we multiply 7 times 1? Okay, so what's this guy's derivative?
44x.
Okay, I like it. Does everybody start to see how insanely nice this rule is? And what's really good about this rule is it extends beyond whole number powers. It actually works for every power, period. I don't give a shit what it is. So for example, what would your guess be? Let me box these off. For the derivative of, yeah, let me start like this. Square root of x. I think if you get further in mathematics, you start to appreciate my rant about radicals that I wish they never were invented. They're dumb. For us in calculus, do we have a rule explicitly for the root of x? No. The only rule we have right now is x to the n. Could I rewrite this as x to a power?
Yes.
Yes. What would that be? So radical notation sucks. It's bad, okay? But it's there, so too bad for us. This makes so much more sense. So what is the derivative of this?
1/2x
Yeah, 1/2 x
to
to negative 1/2. Kick ass. Okay, maybe. And let's just verify this real quick. Not really verify it. Can everybody just draw, let's see, 0, 0, 1, 1, 4, 2. So this is a really, really pathetic scale I've just done, but we'll be okay. And I think I made this point before, didn't I make this point at some point? That the radical actually comes in and kind of goes infinite right there? I feel like I made that point before. Because sure enough, what's the slope at 0? What's the slope at 0? No. What's the negative power mean?
1 over x.
Flip. So when I plug a 0 in, where is the 0? On the bottom. So therefore, what is this going to? Infinity. Positive infinity, because that's one, and that's going to be positive. So, because it can only come from the positive side. So this would go to infinity. And sure enough, right at 0, it's straight up and down, because it starts like this, and then it goes, oh, okay. If you had to guess, the slope at 4, do you think it's very big? But is it positive? Do you all agree that the slope is always positive, but it just really, really gets small pretty quickly? But this will go to infinity eventually. And it's not even the slowest function to do so. So what is the slope at 4? How would you figure that out? I basically just told you. What's the point of this function right here? You all agree this is a function? What is its purpose?
This is slope of h of x.
Pass the butter. No. Huh?
To give us the slope of h of x.
Yeah, it gives me the slope at any point I plug in. That's its job. Because what does that symbol there mean? Derivative or slope. So this function's job is to give us a slope of whatever we feed it. If we feed it 4, what do we get? Let me see if you guys are cool with this. What's the negative power mean? Flip. So what's the square root of 4? 2. Flip it. 1/4. So it's positive small. That was our prediction. We can't predict 1/4 exactly, but it is positive small. And what happens if I keep going and put bigger numbers in? The slope is gonna get smaller and smaller, correct? That matches exactly with what we see. Is that a proof that it's 1/4 of one? No, but it's a good verification. Okay, maybe. Okay, I don't know if you guys understand how powerful what we just did was. It's insane. For any polynomial, even not even a polynomial, just collection of variables to a power, we do not have to use the limit definition. I could just use the shortcut rule we came up with.
Really quick, the 4's on the bottom because it's the negative power.
Yes.
Okay, awesome.
If you really wanted to, you could rewrite this as 1/2x to the 1/2, and you could rewrite that as 1/2 square root of x. Just to really shove it in your own face that radical's on the bottom. Yes. How are you guys feeling? So here, try this one. We'll do this one together. I got a handout. I'm gonna make you guys. I'll make this the J function. Let's see. What you got, Jeff? All right, here we go. Ooh, I like it. That's awesome.
Is that a -4?
Up here, yes. -4, yes. There's something very important. All right. What's the derivative of this piece? Just this. 8x. What's the derivative of this piece? Yeah, -4 times -3 is. So it'll be plus 12 x to the -5th, yes? Because it goes down by 1. Can you see a lot of pitfalls for us poor humans that try to do too many things in their head? You think down when you're like it is 4, but it's got to go to 3 then. No, it should go to -5. But if I start doing that shit, here's a mistake. All right, I'm gonna make a mistake. Everything looks great so far, and I go, oh, it's supposed to be like a power. Okay, what mistake have I made? This is the derivative. This, have I done the derivative yet? No, but people do this all the time. They go, oh, I know, oh, that's supposed to be that. And then you start doing shit with this. You're like, you're not done. You didn't do this guy's derivative yet. So don't do that shit. Rewrite it so everything can be done. And by the way, I kind of went past that. Powers are powerful. Roots are on the bottom. Bam, bam, yes. So what's this guy's derivative? Okay, this is easy. We just did this one. What happens here?
4/3 x to the power of 1/3.
Now here's a really cool little thing. Some of you guys won't need this. But if you take the derivative and you have a fractional power, what is 4 minus 3? And then you put it back over 3. When does that work? All the time. Every time. So very quickly. So this is the derivative. What does this tell me about this function before I keep going? What does this tell me about this function? It's the slope of this function at every point on its domain. What is this guy's domain? This could be a little evil, but is this guy cool everywhere? Where's he not cool? Where's this guy right here? This piece. Is he cool everywhere? This piece? He's cool everywhere. Yes, that's proud. I can square anything I want to. Yeah, even if it's complex. I square. What about this guy? Is this guy cool everywhere? No. Where's he bad? Where's he not good? 0. Can't handle 0. Correct. And what about this guy?
He's cool everywhere.
He's cool everywhere. Cube root can handle all kinds of shit, but x to the 4th is positive anyway. So this guy's domain is everywhere except 0. So and this guy happens to have the same domain. Now, I think I told you guys when you take a derivative, the domain could get a little more restrictive. So we'll see that in a minute. Here, we'll see it right now. So what about this? Let's go back to F. 512, that would be divisible by 3, so let me do this. I didn't really make the one I was thinking about earlier, but too bad. Just want to point out the usefulness of the shortcut. What is the first step in the derivative of x to a power? First step's easy as shit, yes? You just take whatever this is and you write it first. Now if you use the shortcut, the power, if you take this minus this and then put it back on top of this, I really want you to understand, because aren't I going to do minus 1? Yes? And to do minus 1, don't I have to have a like denominator? And won't the like denominator always be this? So don't I actually subtract this from this? If I still didn't screw doing that shit all the time, just do negative 147 minus 113, which is what? 260 over 113. So taking the derivative of fractional power stuff is easy as shit. We'll take the derivative of any power stuff is easy as shit. How we feeling out there?
Pretty good, Jeff.
All right. So what is the derivative? Do have to get to of this? Is it in the form of the rule? So I'm going to analyze it, overly analyze it one way, and then talk about it an easier way. How many x's are here? Do you all understand I could write this? And I haven't changed a damn thing, because that says there's 0 x's. What is x to the 0 power? 1. Kick ass. So can I use the rule? Yes. 0 comes down. Power goes down by 1. What's 0 times anything? 0. Done. Yay! And of course, why does that make sense? If you were to graph y equals 7, what would it look like? And what's the slope of this?
0.
Okay? That's what I think most of you guys would think was beautiful tears, right? You don't have to do work for the derivative of a constant, it's just freaking 0. It's got a 0 slope. Like over time. So, we're almost to the break. So let me give you this. We'll do a couple of things. We'll take a break and we'll reconvene downstairs. So probably what I'll do is we'll pack everything up, we'll move downstairs, we'll take a break, and then we'll go back to that room. Is that understood? Okay. I just gotta remember to put a note in here for next time, for tomorrow.
It'll probably help. Okay, sounds good.
I totally forgot to do the one thing. Oh, well. So just to point it out, there's the better version of what I was trying to write earlier. Right there. Here's some rules. So we've already used this rule, and why does it make sense? Because what are derivatives built from?
Limits.
Limits. So they kind of inherit all the limit rules. So the derivative of a sum of functions or difference is the sum or difference of the derivatives of the function. It's like a limit. Looks like it distributes, but it doesn't because it's not multiplication. The derivative of a constant 0, we just talked about that. The derivative of a constant multiple function, the constant multiple just kind of comes for the ride is what I like to say. If there's a constant in front, it just comes for the ride. And then this is the one we just developed. I meant to do this before I gave this to you, but that's okay. Oh, shoot. This kind of sucks. It's too bad, Jeff. You and your memory. Oh, wait, there it is. Do you guys remember? I'm pretty sure I've already told you this. Sine of a plus b.
Yeah.
Good lord. Sine is the nice guy, right?
Yeah.
Sine A,
Cos B
cos B,
plus sine B cos
sine B,
A.
cosine A. It's like, let's take turns, and cosine's like, yeah, whatever. So if I want to do the derivative of sine x, can you see how I'm going to have to apply that rule, right? So just in case you're looking, yes, go ahead.
Sorry, was that sign B?
This is trying to be a B.
Oh, the one at the end.
Yes.
Oh.
B is one of many, many letters I can't make well. Which other ones are they? All of them.
N
Okay.
H.
All of them. So this would be, so all I did on the paper, the next step, is I used the rule. Now real quick, as h goes to 0, what does cosine h go to? Yes. So this would become sine x plus sinh, no, not sinh. That's why I put h in parentheses, by the way. Believe it or not, sin h is a function. It's called the hyperbolic sine. We'll talk about it later, yes.
Could you zoom out just a tiny bit?
Okay. So of course these two cancel, yes. Now here's where things get trippy. And here's where right now we're just gonna have to kind of like accept it. Not really accept it, but as h approaches 0, sine h over h goes to 1. And you can see that if you graph it, you can see that if you make a table of values. You can see that even if you just do it. Can you guys tell me, does anyone have your calculator? Is it in radian mode? Tell me real quick, what is sine of 0.01? Make sure it's in radians. Sorry, do it again.
0.0099998.
And if you rounded that, what would it be? 0.01. So when x gets really small, sine x is approximately the same thing as x. We actually use this all the time in physics when we talk about pendulums. If we say that we just move it a little bit, this idea that the sine of an angle is roughly equal to the angle itself makes things a lot easier for us. All we have to know right now is the limit of this, don't forget your limit, John. This goes to 1. So what do I end up with? These kill each other. This goes to 1, so I end up with cosine. So the derivative of sine is cosine. Yes?
Is it exactly cosine or is
It's
it more or
exactly
less?
cosine.
Okay.
Exactly cosine. So this, we have to kind of right now take a little bit on faith.
Okay.
By observations, by looking into the graph, but then you could say maybe it's actually 0.9. No. Maybe it's not 1. But it is 1. Later this semester we'll prove it. So if I give you sine x, its derivative is cosine x. So then you might say, well, is the derivative of cosine x equal to sine x? No. And very quickly, if I'm going to graph sine very roughly, what's the most important thing to start at? 0. Good. And then it goes up, and then it goes back. If I was to kind of estimate this guy's slope like we did in section 2.8, what's this? Where's it 0? Isn't the slope 0 here? And the slope is 0 here, correct? And the slope is 0 here. Okay. And in between here, it's positive, and roughly here, it kind of like gets the most positive slope, and then it gets less and less and less. Is that cool? And then here, negative slope. In here, it's the most negative, and then it goes to, what does that look like? The purple one is cosine. If you accept that the slope through there is 1, and that was that one step that we had to do right now based on observations, not proof. So very quickly, what we just uncovered is that the derivative of sine x is cosine x. Now if you graph cosine x and try to do its derivative, you'll start to understand that the derivative of cosine x is actually negative sine x. All of the co-trig shit has negative answers, which is one reason why they are the cotrig shit. Anybody ever freak out about the fact that tangent and cotangent go together, but sine goes with cosecant, and you're like, what's wrong with these math people with this shit? Yes? Well, in calculus, you start to understand why there's some deeper meanings into why we chose the cos stuff the way we did. Yes?
So then derivative of negative sine would be negative cos. And
Yes.
then it would be back to sine.
Derivative of negative sine would be negative cos. The derivative of negative cos would be sine.
Cool.
We'll get deeper into that later. This is me doing stuff a little early. So before we take a break, I'm sure some of you guys have already done these. Can you just try the first 3 of these if you haven't done these already? Alright, the first 3 should be pretty quick. What's the answer for x to the 5th? Of x to the 4th. What about this guy? Kicking the ass in. What about this polynomial thing going on? Yeah, so like if we apply the rule, the 1 comes down and the power goes down by 1, so now it's x to the 0. But if you look at 2x minus 9, do you guys agree that part of this function is the function 2x minus 9? What does this mean? Derivative, which means slope. What is the slope of 2x minus 9? 2. So this is going to happen very often in this class, all math classes. Sometimes if you just step outside of the idea and just go, wait a minute, all this is a line. Its slope is 2, I can see that. You don't have to analyze each piece. You're like, this whole thing is derivative. Slope is 2. Done. Which is another reason why that goes to 0, because it doesn't affect this guy's slope. It just affects where he starts. All right, so let me ask you this. It doesn't feel terrible in here, but are there any people that would appreciate the potentiality of a room that will stay cooler?
Absolutely.
Okay, that's all I needed. Because I know I would. I run hot. So what I want us to do is exactly what I said earlier. Everybody kind of like pack up. I'm going to take you down to what will officially be our new rooms. I've got to actually put in for it, so we'll see. And from now on, we'll just meet there. So tomorrow I'll put a note on the board to tell people where the hell we
Negative
went.
9 x to 0.
So if you guys would, we're going down to room 120. Shit, I forgot which one it is. We're going down to that side of the building downstairs. So if you want to start walking that way, go for it, and I'll try to catch up to you.
New room.